Okay, so in this video, we will be discussing the proof of the quotient rule using the limit definition of derivatives. One thing to note is that I will use the basis with how we prove the product rule in this proof. So let's start with the definition for derivatives using limits. So let f be a function. The derivative function f prime is the function whose domain consists of those values such that the following limit exists. So f prime of x is basically equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now on part 1 of the proof, we want to show that if j of x, suppose we have a function j of x equal to f of x over j of x, then j prime of x is basically f prime of x times g of x minus g prime of x times f of x all over g of x quantity squared. Now to make this easier, what we will do is we use substitution, and our approach here is to treat g of x as a substituted function in product form. So instead of saying f of x over g of x, what we will do is we will rewrite this by letting m of x equal to 1 over g of x, provided that g of x is not equal to 0, and we can say that the derivative of j of x is basically f of x times m of x, since m of x is 1 over g of x, which is just equal to original f of x over g of x. Now, for the part 1 of the proof, we want to show that j of x equal to f of x times m of x implies that j prime of x, or the derivative of j of x, is equal to f prime of x times m of x plus f of x times m prime of x. We start by applying the limit definition. So in that case, j prime of x must be equal to the limit as h approaches 0 of f of x plus h times m of x plus h minus f of x times m of x all over h. Now, we add and subtract a term, f of x times m of x plus h. Now, you may ask, how did we come up with this term? So, it really comes down to your creativity and remembering what our goal really is. Now, our goal is to be able to isolate our f prime and m prime in such a way that we have enough terms in the end. So, really, the basis of this is to add something that still makes the equation true. Now, in this case, what we can add to this expression is really an addition and subtraction of f of x times m of x plus h. That way, you will see how this actually allows us to factor out a common term. So, adding and subtracting a term, f of x times m of x plus h, will give us this following expression. So, you can see that when we add and subtract this term, this basically cancels out to 0. This is just basically equal to 0. Now, this is valid because we're not really doing anything that's changing the original expression. So in this case, this must be valid. Now, you will see how this proceeds. Now, given that, we can actually factor out m of x plus h and the f of x. And rewriting the function by factoring, we get m of x plus h times the quantity of f of x plus h minus f of x. Now, you can see how this quickly is the definition for the derivative of f. Now, we can, on the other hand, we can also factor out f of x times the quantity of m of x plus h minus m of x all over h. Now, remember, our goal is to isolate f of x and f prime of x. And then with that, we can actually, using the limit, the addition rule for limits, we can actually separate h. We can separate the fractions into this form. So we have the separation into two limits, since they share a common denominator h. Now, in this case, on the left hand side, we have the limit as h approaches 0 of m of x plus h times f of x plus h minus f of x all over h. This is very interesting because actually, if you separate again m of x plus h strategically, you can actually use the product rule for limits to make this m of x plus h over 1 times f of x plus h minus f of x all over h. And then, with the product rule, you can separate this two. On the right hand side, we could actually apply the same method. we can isolate f of x from m of x plus h minus m of x by applying the product rule once again for limits. So in that case, what I can actually do is, this is what I did. I essentially separated them by their denominator. So I have m of x plus h over 1, and then this. Also for the right hand side, just the same thing. And this evaluates to, using the product rule, we can separate this limit into this. So essentially separate to two limits. Now, something interesting really happens here when you see that by direct substitution, this is actually evaluated to m of x, because when you substitute 0 to h, you get m of x plus 0 over here, which is just m of x. Now also, this, we have achieved our goal to separate f prime of x, which by definition is here by the limit definition. And also we've been able to separate f of x and m prime of x, and by definition they are separated here. So further simplification, we get m of x times f prime of x plus f of x times m prime of x, which if just for formality, so we get the same structure, we can rewrite this as f prime of x times m of x plus f of x times m prime of x by the commutative property of multiplication. So this completes part 1 of our proof, where we wanted to show how we can transform g of x into product rule form. For part 2 of our proof, we want to find m prime of x, so we can finally express j prime of x as with respect, of course, to f of x and g of x. Now for part 2 of our proof, we find m prime of x by the limit definition. Now remember, on the first part of the proof, we've let m of x be equal to 1 over g of x. So by the limit definition, we can simply say that m prime of x is equal to this limit definition for derivatives, and then simply substitute our values. So m of x plus h is basically equal to 1 over g, and m of x is just 1 over g of x all over h. Now if we combine these two fractions, we get g of x minus g of x plus h over g of x plus h times g of x. This is just basic algebraic manipulation. So we get the following. Now remember, this thing divided by h is actually just equal to this thing times 1 over h, right? So what we can do is actually express that as a separation. So remember, if we multiply something, in this case, g of x minus g of x plus h over g of x plus h times g of x from the previous slide, what we can do is actually swap the numerators and denominators in such a way that we're able to have some sort of derivative. So this is really just creativity. So what we get is the limit as h approaches 0 of g of x minus g of x plus h over h, where this originally was 1 over h, times 1 over g of x plus h times g of x. Sorry, this shouldn't be here. Okay, so what we can do is we can see that we actually have g of x plus h and g of x here. So how do we manipulate this to become g of x plus h minus g of x? Because this is not in the correct form. So what we can do is actually multiply this thing by negative 1 over negative 1, which is valid because we're just literally all we're doing is essentially just multiplying by 1, because negative 1 over negative 1 is just 1. So copy this over, so we get this. So if we multiply negative 1 over this grouped expression, what we get is actually this becomes a negative. This becomes negative g over x plus g of x plus h. So what happens essentially is we get g of x plus h minus g of x over negative h times this limit, just copy it around. So what's interesting is that we can actually see that we're almost at the limit definition for the derivative of g of x. However, we still have a negative denominator at h. So what can we do? Now remember, if you have a denominator of some negative, in this case negative 1, what you can actually do is separate negative 1 as a whole constant. So in this case, what you can do from this one, you can put out 1 over negative 1, or that's basically just negative 1. Copy this over. So we get the limit as h approaches 0 of 1 over negative 1, and proceed. Actually, remember, 1 over negative 1 is just negative 1. This is valid. So, this is basically splitting the limit once again. And what is the limit of a constant? That's just the constant itself. So 1 over negative 1 is negative 1. The limit as h approaches 0 of negative 1 is just negative 1. This is, remember, the limit definition for the derivative of g of x. So we get g prime of x times the limit as h approaches 0 of 1 over g of x plus h times g of x. Now, what's interesting is that if you substitute 0, you actually get g of x plus 0, which it just essentially evaluates to g of x, 1 over g of x times g of x. So, basically, we get negative 1 times g prime of x times g of x times 1 over g of x times g of x. So, basically, you get m prime of x, which is equal to negative g prime of x over g of x squared. So, essentially, we've arrived at our goal to represent m prime of x with respect to g of x. So what we can do from here is that now that we have m prime of x, remember in part 1 of the proof, we have shown j prime of x is in some form of a product rule, f prime of x times m f of x plus f of x times m prime of x. And recall that we've let m of x equal to 1 over g of x, and on the part 1 of the proof, we've shown that m prime of x is equal to negative g prime of x over quantity g of x squared. Now, what this tells us is that if we substitute m of x and m prime of x, we're finally able to get full on g prime of x with respect to f of x and g of x. So what we can do from here is simple substitution. M of x equal to 1 over g of x. M prime of x is negative g prime of x over quantity g of x squared. Substitution, we get the following evaluation. You can go and check this for yourself. So finally, we get the g prime of x equal to f prime of x times g of x minus g prime of x times f of x over quantity g of x squared. So by the limit definition of derivatives, we have shown that g of x, if g of x is equal to f of x over g of x, then g prime of x is equal to the following quotient rule. So what this tells us is that we are now finished with our proof because we've achieved that g prime of x in the quotient rule definition for g prime of x. So this concludes our proof.